welcome on to session 2 here. We'll be kicked off by Phil O'Leary, talking about the issues of excess moisture in mass timber, and really this is the focus of the day really in terms of identifying this potential issue that we have, and the next couple of sessions about how we identify the issue and then all about how we work with it to mitigate the risk. So,
okay, thank you, John. I based this on purely empirical evidence. I've been a consultant or timber technical consultant for over 30 years and I've inspected hundreds, not thousands of buildings of all sorts. So this is all kind of stuff I feel. I do actually feel after 2 positive talks, I feel a bit one grim reaper here coming to the, but it's not that at all. I love CLT, these big buildings. I never had a sports hall like that when I was a youngster, not that I remember. But so I'm going to look a bit about moisture and the sources. So we know that we have construction moisture, it rises surface moisture, and then we need to know what happens to it, how it runs, does it get trapped, and where it goes. So that's the start of the build process. And then we have leaks, and we've historically put leaks as either coming from external fabric or internal services. And then we have practically those, are they slow leaks or are they large water events? Because they have a profound difference in what we see. And of course this affects, whether it's roof, walls or floors, it kind of affects them all in the same way in terms of water. I've got this diagram from the Mass Timber Institute of University of Toronto, which I think is quite a good example. It shows you that we've got water from interior moisture, construction moisture and exterior moisture. But what it shows you I think is really good is how do we lose that moisture? It shows 3 ways. That's basically the 3 ways we've got, assuming we're not adding heat to some system. And you'll see the largest by far is drainage. Then we have ventilation and evaporation. And the slowest, and it really is much slower, is capillary distribution and how that comes away. So it's no surprise that when we design with timber, we've always talked about drainage and ventilation. It's obvious reason why, because they're the 2 systems that work. And what we're interested in is just the 20% decay threshold. So we know that timber, if we keep the moisture content below 20%, it won't decay. In reality, it's probably nearer 25. Timber decay won't really initiate until you hit about 25. Although timber around 20 to 25 can carry on decaying if it's decaying. So what happens to water is a typical example of just some surface water lying on a CLT. And what we're concerned about is 2 things really. How much water is there and how long it's going to stay there and where it's going to go. So in an ideal world, it would just evaporate. And it will depend on a number of things that depend on the timber species, how durable timber species, it'll depend on the weather, whether it's raining more, whether it's windy and all that kind of stuff. But if I looked at a simple roof like this, or I have a slope, obviously the water will then run down, but then it will drain. But where will it drain to? And if it drains to that kind of area, then we get concerned as to where that water goes and how does it behave. And if we reduce the rate or remove those above mechanisms of drying, we get very concerned as to what happens to the water when it gets there. Yeah? So we've seen this countless of times where we've got sloping roofs and a parapet wall. I'll come back to that a bit later. I've been studying for probably 25 years how water moves in timber. I did it as a graduate and as a master's. They did quite a lot of work on testing this. So we talk about the permeability of timber, and when I talk about permeability, I'm talking about the rate at which solid water and vapour moves through the timber. And it varies significantly with timber species. So timber species like spruce, which we use a lot of in CLT, is actually fairly impermeable or very restricted. And it's one of the reasons, for instance, why highway agencies won't allow spruce to be used as fence posts, because we can't get preservative treatment enough in it. So that's a positive, but it's also a negative, because if it does get wet, it takes much longer to dry. We also have parts of the timber like sapwood, which I used to call the living part of the tree, and someone corrected me the other week, said I think it's the active part of the tree, and I thought it's probably a good description. And blue stain, and it does affect, so that increases the permeability significantly. So we can't see that well, but here I've got some panels of blue stain, and you'll see these dark areas here. and actually we can't see very well, but it's 2 areas of heartwood. And when we've soaked it for a long time, we can see the difference in uptake by where we've got blue stain areas and where we've got sapwood. And where we've got heartwood, we don't take much up at all. So these areas are heartwood here and there. Is that important? It is, but it has nowhere near the significance about the rate or the permeability of timber in the 2 grain directions. So obviously a tree is designed to conduct fluids up and down itself, so therefore it's no surprise in that it's much more permeable along its end, along the grain as opposed to across the grain. There is differences across the grain, but they're very small compared to them. There's people like Smith and Lee wrote papers in 1958 which suggested that the vapour permeability along the grain was up to 10,000 more than across the grain for some timber species. And there's further work that's been done in the 1970s, people like Comstock and Bolton, not unique, but who have shown that it's of several magnitudes greater than that really. Okay. So we then know that if we look at CLT panel, we know that the timber or the water is going to predominantly move along the grain. Yeah, so laminates 1, 3 and 5, or the top, middle and bottom, we're going to get much more moisture. We've also got the glue that plays a part in stopping it from going from one to another. So we know that's what's going to happen and that's what we get. So if I go back to my wall, my water running down, what issues do I have? If it's open like that and it's able to drain or able to ventilate, it might be okay. But what happens if I then enclose it, as happens, and the kind of pattern we get that, so it's the kind of pattern we see typically all the time. So we've got water at the top, it hits the end grain of the parapet wall, and the parapet wall will take it up differentially depending on those orientation, those laminates. I can go into the building and take moisture contents at the bottom, and all I find is a moisture content of 8 to 12. Typically 12 in a building this size, but if I go into a big sports hall, typically it's down to 8 or so. But unless we do some investigative work, what we'll find is that the moisture content here will often be 20 plus. Okay, so that's an issue that we can't see. So when that happens and it lasts for a long time, we end up with things like this, where we get a total decay of the top laminates. Yeah? And you'll see here, I'll show the next photograph, we can see where this is actually a CLT beam, and you can see the middle laminate, which is vertical, is taking up a huge amount of water compared to the others. And if I went further along, you can see that the 2 laminates that are running that way are perfectly okay, but this one's actually decayed to a depth of about 400 mil, simply because it takes moisture up in that direction. Okay. So if we have leaks, what tends to happen is an example of a school where we had lots of leaks, and you can see the water's tracking across this way. But then when we kind of looked at it, we actually found that the depth was probably only 1 laminate depth. Put underneath, we couldn't see a thing. And what we technically see is just see that, where we've got the top laminate is totally decayed, but a second and third might be okay. Depends how long it's been wet for. And going back to the previous one, when they did some repair works, we were able just to simply route out the, I say simply, it's a bit difficult to route out just the top level and do repair works. Okay, so if I look at a flat roof and we've got areas like that, we've got lots of water, it's fine until it gets wet. So what kind of distribution do we get in timber and flat roofs with elites? We tend to get this kind of distribution where we've got water at the top. It may come down at the joints, or one we often see is where we've got a joint and maybe a plywood splice at the top. Yeah? So this one here, from underneath, it looks like that, whereas this one here, it's given us a bit of a clue. So sometimes we'll see some water staining running down a joint simply because the water's been able to come across. But also, because when water comes down, what do you think happens to this water? It then goes along the grain of those laminates. Yeah? So we see that like that, but then when we open the roof, we end up with that. So the point I'm trying to make, it's actually very difficult to see the damage. So CLT, because it's mass timber, it's very, very good at hiding water damage. Okay. So we can have damage caused by construction moisture. Myself and a number of ex-colleagues here will tell you that it's an incredible number of roofs that we looked at 5 to 7 years after being constructed, where the top laminate or sometimes the top 2 laminates are totally decayed, but the timber's perfectly dry. Okay. Then we can look at the leaks, whether it's poor workmanship, whether it's penetrations, whether it's windows, whether it's, we've seen balustrades of balconies and things penetrating the CLT, which leads to ingress of water. It just spreads along those things. But once we've got CLT in a building, and if it's wet, whether it's a leak or whether it's construction moisture, we've lost our two major forms of drying, which is drainage and ventilation, evaporation. Therefore, we're down to diffusion. The diffusion's a very, very slow process. Okay, so once this gets wet, depending how wet it is and how thick the timber is and how much is wet, we're talking about months, if not years, for it to dry, assuming we've stopped the water source. Okay, so what we get very concerned about is how long above 20% moisture content has this been. Okay, and that's what we don't know unless we start inspecting buildings. But most of the time we don't know we've got a problem. Okay, so typical moisture gradients you might find is the top is 40, 25, 15, 12. So from underneath it looks nice and dry. Slightly worse, we might have 180, 40, 18. I put 100% there, but moisture content can be more than 100%. Things like spruce, we did some test work where we tried to work out what the maximum moisture content of spruce could be. And it's about 140 to 250%, so it could be more than that. And I came a much worse case scenario where I have 180, 60, 40, 25. I'm going to ask you to remember three numbers or write them down. This one's 3, this one's 16, and this one's 33. If I have this happening, what can happen obviously is we can decay through the whole panel. Yeah, and we have seen it. And you can see that even on the left-hand side, it's totally decayed, but it's hidden. This one here was actually a school where there was a football pitch on top of this. And the only reason they found out about it is because people start thinking, this is a very bouncy football pitch. So we did this. So this is what happens. Yeah? So here's one example, etc. So you'll see that at the top there, we can see decay in the wall and in the roof. Yeah? So the roof panel's 100% decay at that point, more or less. The top of the wall panel is also significant decay. But what is worse, and what we don't see, is that at the back of that panel, the water's run down. So a 90 thick panel has only got 30 to 40% left of that cross section. And what gets worse is at the bottom, where the water's run down, I've got CLT, this one was actually at ground level, the base of ground level, so the water's tracked down and it's gone 7, 10 meters in both directions. And the bottom of that panel is 100% decayed, even though you can't see it. Okay, so that's the kind of things that we do see. We'll see leaks quite often, but we do see them. And again, it's all this slow leak that happens, so we can't see it happening. If someone decides, oh, this floor actually feels spongy. If you've got quite a rigid floor, we don't see that. So by the time we come to that, we've lost 30, 40, 50, sometimes 60% of the floor integrity. We'll see leaks in windows. And what we're concerned about, yes, we can see it, but we're concerned about where's that water gone down the wall. Okay. I've seen leaks in a corner of a 3-story building, and it looks like it's just come down one side. It comes all the way down, and we can see it was decayed. And then we look at behind the skirting boards, again, for another 10 meters, 100% decay, where that timber's water's just come down and it just tracked along. Okay. Here's an example of a floor with a leak that started 4 meters away. The water's straight on. And what you can't see very well, we've got fixings there which are corroding. Okay. Again, that had insulation and chipboard and another layer on top. They knew nothing about it until people start thinking this feels very, very spongy. Okay, so here's another example of an external wall. That's what it looked like on the inside. That's what it looked like on the outside when we convinced the contractor that actually the back of that was decayed and it was caused simply by a leaking box gutter. But they didn't know about it because they couldn't see it. So that's the problem with CLT, is that we're always having to find these things that we can't see. So the base of walls, time and time again, here's a wall. There's a plaster board, 25mm gap. CLT in that condition is 150mm below ground level. And if they've had a leak, they can just see that. But the leak's been on for so long that, again, we've got 4 or 5 metres of totally decayed timber at ground level or below ground level. And once we start taking things off and relieve them, we just see time and time again at the bottom of CLT walls that are in or below ground level, where the water gets trapped, we get that. And we can't see it most of the time until we start really looking at it. Yeah? So if I have toilets at things at ground level, and we've got CLT again below ground level, then water goes in and then it just sits there, and without the occupant or the building owner knowing, it just decays over time. And we end up having to do some kind of fancy repair sometimes because we've got the walls got nothing supporting it really. So we've seen examples where we had to cut decayed timber out, and again we've decided, or they decided, that I'm going to put it 150 mil above ground level. So it ends up being on a concrete kind of plinth just to give it. Had it been like that at the start, they would have probably been okay. So people will argue that we should or could have timber at ground level or below, but I think it's a risk you decide to take. I've inspected hundreds of buildings where we've got, we drill a fine drill bit, it goes down 300 mil, I did 300 mils, 150 mil below that, and it's dry and sound. So it does work, and it does work, but it only works when it works. So there's always a risk that once you've got this timber that isn't going to drain, isn't going to be ventilated, what do we do when it gets wet? Okay. So, to conclude in a way, we know the mechanism, we know how it dries and doesn't dry, and we know that we've got to keep below 20% moisture content. So we know all these things. We know the difficulties in identifying wet areas because we can't see them. We know also that when it does get wet, it takes months, if not years, to dry, depending how wet it is. It gives us huge challenges to repair and expense to do so. So although mass timber's got lots of advantages, one of its main disadvantages is that, one of the main advantages is that we can't see the majority of damage, or we can't see at the early stages. Okay, and also, when you think about how long the water takes, those figures I gave you was that first panel, a square metre of that panel of 160 mil depth, that 3 meant that square metre had 3 kilograms extra of water than when it was manufactured. The 16 meant it had 16 kilograms of water in that square metre. And the third sample, 33, meant that for every square metre, I had 33 litres of water more than we started off with. So you can see the issue of how difficult it is to dry. You can see also how much weight it puts on the roof, because you start doing roofs that are 10 metres by 6 metres, you're suddenly having potentially 2 tonnes extra of water on the roof alone. If you ever ask a scaffolder about moving or putting up wet scaffold boards as opposed to dry scaffold, they'll tell you how difficult it is. So we do know all this, and as people have alluded to before, that with all this knowledge, we can and we should be able to get this right. There will be cost to it and there will be difficulties, but surely it's better than ending up where we're going. And one final point I'd like to leave with you is that what we don't know how many buildings look okay, have got some kind of problems. Some might be serious, some might not be so serious. Okay, thank you.